Hello everyone. In this video I wanted to go over a couple of example problems in conservation of energy. A couple of them will be dealing with conservative forces and one of them will be dealing with non-conservative forces. So with any other conservation law in physics, such as mass or momentum or total mechanical energy, what we're saying is that the quantity that you start with has to be there through the entire problem. And dealing with conservation of energy, the total mechanical energy, that is to say the kinetic energy plus the potential energy, is conserved as long as there are no non-conservative forces such as friction or air resistance acting. So the equation that's here, the potential energy before plus the kinetic energy before equals the potential energy after plus the kinetic energy afterwards, kind of expanded out here. This is that general form of conservation of mechanical energy when non-conservative forces are acting. So first, when we have non-conservative forces, just the force of friction. Here we have a roller coaster at the top of a hill, and it's initially moving at 0 meters per second. It dips down to 25 meters below, and then finally levels out 20 meters below where it started from. And what we're asking for is what is the final velocity over here. And here we have the frictional forces is negligible, so in other words we can sit there and ignore it. The roller coaster loses potential energy as it goes down the hill. We're going to neglect friction, so the force that is going to end up doing work on it is gravity alone. And the loss of gravitational potential energy from moving downward through a distance h is going to equal the gain in the kinetic energy. So with this, another way to sit there and think about this is we have some potential energy here and we have some kinetic energy here. And with that in mind, we can sit there and we're just interested in the vertical height that it falls. And there's no kinetic energy to start with, or there's no kinetic energy and there is some potential energy. And afterwards, we're going to say that there's no potential energy and all this kinetic energy. Now, the 25 meters is a bit of a distractor here. We're really only interested in the height above what the finish area, which we're going to call zero potential energy. But then we can just set mgh is equal to 1/2 mv squared, and we can solve for the velocity, which is just equal to the square root of 2gh. And plugging in the values that we have, the velocity is equal to the square root of 2 times 9.8 meters per second squared times 20 meters. And with that, we end up seeing that the velocity is just 19.8 meters per second. So that is a relatively straightforward problem. But what if, we're extending this just a little bit here, we sat there and we are asking once again for the final speed, but this time the object is moving at 5 meters per second to start off with. And again, we're going to ignore any frictional forces. Well, what that means now is that in looking at the solution, the energy before equals the energy after. That statement is still true. But now we have some potential energy and some kinetic energy. It's elevated above our zero level, and it's moving. And then afterwards, all we have is kinetic energy. So we expand this out. mgh is equal to 1/2 mv initial squared is equal to 1/2 mv final squared. And yes, the colors do matter here. And then therefore there's a like term of mass in each of these. All of these masses will have to be the same, so we can cancel those out. And with that, if we multiply both sides by 2 to get rid of the 1/2 on the after side, we end up with 2gh plus the initial velocity squared is equal to the final velocity squared. Now some of you might say, well, wait a minute, Mr. Lovering. This right here, that looks kind of familiar. I've seen this somewhere before. It's one of the kinematic equations. We just replaced g with a and h with delta x, and it's one of the kinematic equations that we looked at before. And yes, this equation is very similar to the kinematic equation that we gave before, but it is more general. The kinematic equation was valid only for constant acceleration, whereas this equation is valid for any path regardless of whether the object moves with a constant acceleration. Now substituting the values in that we know, we get a final velocity of 20.4 meters per second. This solution sometimes seems rather surprising, that if we started off with zero velocity, we would have obtained a velocity of 19.8 meters per second. And you might think that if you were going at 5 meters per second to start off with and you're going down the same hill, that you would just add 5 meters per second to this and that would be your final velocity. But that is not the answer that we end up getting. As a matter of fact, it's not even a meter per second faster. It's like, where'd all that extra energy go? And one of the things you kind of, in order to explain this, you kind of have to understand the fact that kinetic energy increases with the square of the velocity. In other words, if we plot out kinetic energy along the y-axis and then the velocity along the x-axis, we get a parabola. And again, if you think about it, 1/2 mv squared, kinetic energy being your y value, and then velocity squared. This is a similar sort of equation to y equals x squared. So if we look down here, we have the change in velocity, just sort of generally labeled here, but let me throw some numbers at you here. If we go from, say we're going to make the change in velocity 5 meters per second down here. So we're going to go from 2 meters per second to 7 meters per second. Well, the change in kinetic energy only ends up being this much here. We go from this value to this value, so we've increased the kinetic energy by this much. If we go over here, where the velocity is much larger to start off with, say we start at 22 meters per second, and then we go to 27 meters per second, we have the same change of 5 meters per second here. But because it's increasing as a x squared function, we start off with this amount of energy, and then by increasing by 5, we go all the way up here. So the change in kinetic energy up here is much larger for a change of 5 meters per second. If you've taken calculus and you know what an integral is, this will make a little bit more sense. If you integrate this function, another way to think about it is if you integrate from 2 to 7 for x squared, you get a certain area underneath the curve, and that's one value. But if you do it from 22 to 27, you get a much larger area underneath the curve. And that's another way to think about this. So, all right. So to the last problem, here's one where we have a non-conservative force acting on the object. So here we have, using energy considerations, calculate the distance the 65 kilogram baseball player slides, given that his initial speed is 6 meters per second and the force of friction against him is a constant 450 newtons. So here, mechanical energy is not going to be conserved. Friction stops the player by converting the kinetic energy into other forms, thermal being one of them, sound's another one. But in terms of the work energy theorem, the work done by friction, which is negative, is added to the initial kinetic energy to reduce it to 0. The work done by friction is negative because F is in the opposite direction of the motion. So here we have the kinetic energy minus the work done by friction equaling 0, because there'll be no energy afterwards. And with that, we can solve for the distance that's going to end up being traveled by the baseball player. So we bring the FD over into the other side, and then we divide both sides by the force. We plug in the values that we have here, and we see that the distance that the person's going to slide is 2.6 meters. The most important point of this example is that the amount of non-conservative work equals the change in mechanical energy. For example, you must work harder to stop a truck with its large mechanical energy than to stop a mosquito. Anyway, thanks for watching.
Fixes classes.